how we came to know that the universe is expanding at an accelerating rate?
This attractive gravity is still stronger. So you believe that Andromeda and Milky Way are supposed to merge together somewhere in the future. It can only reach points in the universe which is 18 billion light years from us. So anything beyond that 18 billion light years is part of another universe.
A will spread out.
Yeah, because they are, if they become more intelligent than us, right? Then
A
why
will overtake us.
Exactly. So why do they need us? No, they will find their ways to spread.
So the current human beings will go extinct.
That's one possibility. Maybe not extinct. They'll keep us for some other purpose, right? Just like there are many other animals in the world, right?
The universe is expanding at an accelerating rate. But what does this mean for its ultimate fate? Will it expand forever or rip itself apart or collapse into itself? And what does this mean for our own fate, our own future? Welcome to a new episode of the Science Talk. Today, we explore the destiny of our universe with one of the greatest minds in theoretical physics, Professor Ashok Sen. A pioneering figure in string theory and quantum gravity, he has profoundly shaped our understanding of the universe at its most fundamental level. He was among the inaugural recipients of the Breakthrough Prize in Fundamental Physics for his pioneering work showing that all string theories are different limits of a single underlying theory. He has also been honored with prestigious awards like the Dirac Medal, ICTP Prize, and the TWAS Prize, along every major science awards in India. The nation has recognized his contributions with the Padma Shri in 2001, Padma Bhushan in 2013, and the scientific community believe that Professor Sen would receive Nobel Prize if string theory will get experimental confirmation. Professor Ashok Sen, a warm welcome to the Science Talk. Our last conversation was online, so we are truly honored to receive you at our studio for this conversation.
Thank you very much. It's a great honor for me as well. Thank you.
If we were to narrate the story of the universe like a grand cosmic story, how would you summarize it?
Well, as far as we understand today, the universe started its beginning with some kind of explosion, right? Which of course is what we think it happened, because we have to extrapolate back in time to really know what happened at the beginning of time.
Which is called the Big Bang.
Which is called the Big Bang.
Is it an explosion or an expansion?
Well, we know that it's an expansion right now, but if we just extrapolate it back all the way to time zero, we see that there is an infinite density. Now, we don't believe that the usual laws of physics that we understand today will be valid at that time. But if we extrapolate it back, then it would look like an explosion, right? But we don't really know how it began. Okay. What we do know is its current state, and we can extrapolate back in time for a reasonably long period. And you know, for example, how the universe looked, for example, around 10 to the minus 4 or 5 seconds. But beyond that, we need more inputs, right? We don't really know.
How far can we see into the past?
Well, if we want to know how far we can directly see into the past, we can see the image of the universe when it was about 400,000 years old. Because before that, what happened was that the universe was opaque. Their hydrogen was ionized, their hydrogen atoms hadn't formed, so the electrons were hanging around freely. And they would have scattered light so much that it would have been opaque. So you can't see it in visible light. So that's our direct vision. But as I said, we have reasonably good theoretical understanding of how to extrapolate it farther back in time, because we understand the microscopic physics reasonably well. And based on that, I would say we can see theoretically at least back up to about 10 to the minus 4, 5, maybe even 6 seconds. But beyond that becomes harder, because as you go back in the past, the universe was hotter. So the particles were colliding at very high energy. So if you want to really extrapolate back, we have to know what happens when particles collide at very high energy. And that we know only up to certain energy, right? We don't know beyond that energy, and that's a limitation. which prevents us from going farther back in the past.
So, if we narrate the story from that big bang till now, how will be the story of the universe?
Well, of course, the story evolves all through, but there are some events which are significant. One of the events, for example, is when the protons and neutrons, which are free at that high temperature, they form nuclei. Right? That's one big event, because that physics determines, for example, today how much hydrogen we have and how much helium we have in the universe. Those are the main components of the universe, and that is determined by the physics in the early universe. I say the second big event was when the protons and electrons combined to form atoms, because that's the time when the universe became transparent, because once the electron got bound into the proton, light scattered very little, and so what we see today, this cosmic background radiation, is the image from that time. Right? That happened about 400,000 years ago, and then of course the universe evolved. There are small fluctuations in densities in different parts of the universe, which gravitationally become larger and larger, because the little denser region started pulling the matter towards it. Okay? And that eventually led to the formation of stars and galaxies and various other structures that we see in the universe.
What could be before Big Bang? That's not known.
That we don't understand. As I said, that
Is that we imagine that it's a very tiny dot in an empty space, or there is no space, or all these are emerged from nothing?
yeah. See, all of these, I mean, there are various speculations, but in order to really make a firm conclusion, we need to know what happened at that high energy, because as I said, as you go back far in the past, the temperature becomes larger and larger, and higher temperature means that the particles will have more energy, so they'll collide very energetically. So unless we know what physics was governing the laws of those particles, we really cannot say what happened. Forget about before Big Bang, right? Even all the way up to Big Bang, we cannot say what happened, because of this fact that we don't understand how the particles collided and what happened when during the particle collision.
It's beyond our imagination.
Yeah, right now it's beyond. Well, I would say that it's beyond our imagination at present, but doesn't mean that it's theoretically or experimentally impossible to figure out earlier history, because I mean, we are starting to explore higher and higher energies in particle accelerators. So we'll certainly have better understanding as we progress in science. But to really know what happened at the very early time, right, we need either experimental breakthrough or theoretical breakthrough. Right? Maybe there will be understanding of the fundamental laws of nature, which will tell us theoretically what exactly happened at that time.
So this evolution of this artificial intelligence plus this quantum computer, is there any scope for analyzing the data we received from
I think the question is not that you have to analyze data, because we have data.
We have data.
Yeah, so you have to basically get more data.
More data at that higher energy level, and that seems impossible at this current era.
That's right. On the other hand, it could also happen that these quantum computers and artificial intelligence will make theoretical progress, right? Maybe it will figure out what are really the basic laws of nature, right? In which case we can use that theoretical knowledge to figure out what happened very early in the history of the universe, right? Because once you understand the theory, you should be able to predict what experiments will give us, right? You don't have to actually do the experiments.
That will show the path to an experimental confirmation of
exactly.
Theory.
Once you have a theory which explains whatever you have observed so far, it will certainly have newer prediction, right? What will happen at higher energies, and then the experiment should be able to confirm it.
How we came to know that the universe is expanding at an accelerating rate?
That came from the supernova experiment, right? Because of course we had known for a long time that the universe is expanding, because we see that the farther objects are moving away.
Using the Hubble telescope, we found that the universe is expanding.
Yeah, even before Hubble telescope, Hubble was a person who discovered this expansion of the universe.
It's
right?
read that while Einstein developed his general theory of relativity,
around that time,
he got the result as universe is expanding, but he added a constant,
cosmological constant.
Yes. but he did not believe at that. Hubble discovered that the universe is expanding.
Exactly, right? And so people thought that the universe will expand, but the expansion will slow down because matter is pulling the universe back. Right?
Because of gravity, the matter is
Yeah, matter is pulling
getting
it
pulled.
back. Right? So then one expected that the expansion is slowing down, right? And the way we measure whether the expansion is slowing down or not, that you look at distant, because we of course cannot go back in past. We cannot say what the rate of expansion was in the past directly, right? But you observe distant objects, and that gives you a view of the past, because light takes some time to come from the distant objects to us. So you look at farther and farther objects, okay? And the farther and farther objects basically tell us that, and you look at what is their speed, right? So that told us how fast the things were moving away in the past. So this is what people used, that you look at distant objects, and the supernovas are very good measure for how far they are, right? The supernovas have a property by which, by looking at them, you can determine the distance, and then you can also determine how fast they are moving away, because by Doppler shift. So using that, people figured out that the rate of expansion of the universe in the past was smaller than the rate of expansion today, right? And that's what gave rise to this accelerated expansion. So that's what told us that universe expansion is actually accelerating.
How far into the future can we see?
Well, that depends on our current if the current understanding or the current best understanding of the theory is true, then the expansion will continue forever, right? That's what the theory says, that if it's really the cosmological constant that's driving the expansion of the universe, right, then at least as far as the classical physics is concerned, the expansion of the universe will continue forever.
As far quantum mechanics is concerned?
Once you take into account quantum mechanics, then there are some possibilities that our universe may make transition into another universe, another kind of universe, right? It is like a phase transition. If you imagine glass of water which is cooled below its freezing temperature very slowly, so it may not freeze immediately. It comes to what is called a supercooled state, but then a small disturbance will form small pockets of ice, and then the whole water will become ice. So quantum mechanics tells us that there is such a possibility even for our universe, that our universe is something in a like in a supercooled state, right? And sometime some small pocket of more stable phase may form, and then that will expand and fill the whole universe. So that possibility exists in quantum mechanics, but not in classical mechanics.
Okay. We studied magnetic force, electric force, both are attractive and repulsive. But the gravitational force is attractive only, and this gravitational force holds the matter together. But when these galaxies are moving away from us, so what force drives this away, or how, or the gravitational force acts as repulsive force outside our local galaxy, or
Okay, yeah.
or we did not observe any increase of distance between the planets in our own solar system or outside our solar system within the galaxy. So what about the nature of this force, which
Okay.
the force pulling the galaxies away from us?
Yeah, so all of this is gravity, right? Even before the discovery of dark energy, right? Of course, we knew that objects are flying apart, okay? But that is not conflicting what the even usual gravity tells us, because imagine that we have gone to the moon, right? The rocket leaves us, even though there is gravity between the Earth and the rocket, because once you give it a very high speed, right, it exceeds the escape velocity, then objects move apart, even if gravitationally attractive. Right? So originally the Big Bang theory was supposed to be like that, or thought to be like that, that there is a expansion, that the universe began with a big expansion, big push, right? That pushed everything apart, okay? And then it was thought that the gravity will slow down their expansion rate. Right? That was the standard idea in the Big Bang theory. But discovery of dark energy told us that it is actually repulsive, right? Which was a surprise. But that also can be explained within gravity, right? Because Einstein's theory, in particular the cosmological constant term that Einstein had added to the theory, that has the feature that it produces some kind of negative pressure. And it's the negative pressure combined with Einstein's theory of relativity tells us that universe will actually accelerate. If there is really a dark energy like object, right, and like energy density, which has negative pressure, then the universe will accelerate. So that's also part of gravity. On the other hand, the planets and the stars within a galaxy, right, they are not moving apart because their gravitational force is much stronger than the expansion. Right? The expansion is big in a large scale because the dark energy is everywhere. But the kind of energy that the energy density that the planets and stars have, right, that's larger than the dark energy, right, the average density of dark energy, right, because it's concentrated. And that's what keeps them together. Right? The planets and stars don't fly away.
Inside the nucleus, the strong force is the most strongest force. Then out in the micro world or in the quantum world, the weak forces dominating, or the electromagnetic forces. Then in the celestial bodies, the gravitational force is the strongest. But between the galaxies, this repulsive force is the most strongest.
Yeah, even not even between, I'll say between the clusters of galaxies. Yeah, we could be, see, for example, between us and the nearby galaxy Andromeda, this attractive gravity is still stronger.
Still stronger.
Right? So you believe that Andromeda and Milky Way are supposed to merge together somewhere in the future. Right? But indeed, once you go beyond that, right, beyond this local cluster of galaxies, then this repulsive force is the strongest.
How you arrived at this dark energy, how this concept evolved, what is the story of this dark energy and dark matter also?
So dark matter is easier to explain in the sense that, it's like ordinary matter. Right? And the way this dark matter arose is because people tried to explain whatever we see in the universe in terms of ordinary matter. Right? But they found that that doesn't quite explain everything that we see. Right? One particular experiment that in fact was very useful was that how stars near the edge of the galaxy. So if you believe that most of the matter is concentrated inside the galaxy, then the stars which are moving out at the edge, right, as you go farther out, right, their velocities will have to follow certain pattern. But what people found is that the velocities of the stars don't follow that pattern. That as you go out, the velocities are supposed to decrease, but they don't decrease. They keep at the same, more or less at the same speed. Okay? So that showed us that there must be more matter than what we see. There will be more matter than visible matter. Okay? And that was the first, or one of the first evidences for dark matter, that there is something in the universe which we haven't discovered yet, which is not within the stars and the dust that we know exist. Right? It's more than that. What exactly dark matter is, people are still trying to figure out. Right? But it has properties similar to ordinary matter as far as the gravitational properties are concerned. It has
also gravitational energy.
Yeah, it has a standard gravitational energy. Right? It could have been ordinary matter. It says that we don't see it. Right?
What about the density of this dark matter? It's more than the
it's matter, more than the ordinary matter.
Ordinary matter.
Yeah. For example, for the whole universe, we know that about 70% is dark energy and 30% is ordinary matter plus dark matter, but of which only about 4 to 5% is ordinary matter. Right? So that's very small.
70% is dark energy. 30% is this matter, and among this matter, 26% is dark matter. Exactly. The only 4% is the visible matter, ordinary matter.
Exactly.
Out of this 4% ordinary matter, how far we could see?
I think this we could, we can estimate how much matter is there in the galaxies, right, by looking at the stars and estimating how much dust there is, and that's what gives this 4% number, right? So we do know that this 4%. See, we are thinking in terms of density, right? So it's not that we have to see all of the universe to figure out this 4%. We take a very large part of the universe, and in that large part we see what fraction is what, and there we can indeed identify this 4%. But I think you had asked also about the dark energy. Right? Dark energy is what Einstein had called cosmological constant. Right? So it certainly has been there. We knew of the existence of such a possibility for many years, right? Because even Einstein had written down that. It's just that he realized that that is not needed for the cosmological models that people had at that time, because at that time we didn't know about the accelerated expansion of the universe. Right? But after the discovery of the accelerated expansion of the universe, people realize that it's the cosmological constant which can explain the accelerated expansion.
So this dark energy drives this expansion.
Yes.
So what if there is no dark energy? Can we think that there would be no expansion?
So if there is no dark energy, there could still be expansion, because as I said, even rockets can leave the planet, right? If you give them enough velocity. So if the Big Bang started with a big expansion rate, right, then the ordinary gravity, right, ordinary gravity to ordinary matter will slow down that expansion, but it could still continue to expand. That depends on how much speed you had to begin with.
But this dark energy gives the accelerated
Expansion. Yeah.
So is it a friend to us or an enemy? Because what will happen to the universe due to this accelerated expansion?
Yeah, I wouldn't call it an enemy. It will just continue to expand, right? But it's not that we are going to die because of the expansion of the universe, right? Because we are going to die because eventually our galaxies will run out of fuel, right?
Galaxies will run out of our way.
Of fuel, right? Because the stars will eventually die, right? So we need energy to live, right? And right now we are getting our energy from the sun, right? And some from radioactivity of the earth. Right? So once all the stars die, right, then maybe even the radioactivity of the planets will keep us going for a while. But eventually eventually life will come to an end because of because we'll run out of energy, right? So I don't see that the expansion of the universe itself is going to do anything to us particularly. What it will do is it will, in the far future, right, we will not be able to see anything else in the sky, right, only our galaxy, because everything else will go so far away that there will be beyond our reach.
Single universe or multiple universes. Your theory suggests that all these universes are parts of the single universe.
See, multiverse, different people use this multiverse in different ways. Right? I think the way I think of multiverse is if different parts of the universe cannot communicate with each other, if it's theoretically impossible for the different parts of the universe to ever communicate, then it's like two different universes, right?
Because how can we imagine multiple universes when everything started from a single point like matter?
Yeah. So it's not multiple universes. It's not that there is a boundary between the two universes, right? It's the same continuous universe, right? It's just that if an object here, right? Suppose we are here today, right? And there is another person or whoever somewhere else in the universe, and if it is theoretically impossible for us to ever communicate, then I'll say that you are part of different universes, because.
So if we cannot communicate each other, we can consider us we are from different universes.
Exactly, because even if the whole universe disappears for some reason, right? The part of the universe where that person is living, right? Even we'll never know it. Right? Not just me, but in any distant future, it will be impossible to know what happened there because it's out of communication. This is the definition of the multiverse we accept, right? Then we have already seen the multiverse, right? This is not a theoretical concept anymore, because right now, for example, you can see the part of the universe you can see is about 45 billion light years in radius.
45 billion light years as its radius.
Yeah,
it's experimentally
proven. Yeah, that's for example, the cosmic microwave background radiation we see, that's coming from a place in the universe which is about 45 billion light years away from us. But we also know that today, if we want to send out light signal, right, which is the fastest moving object, it can only reach points in the universe which is 18 billion light years from us. So anything beyond that 18 billion light years is part of another universe, because we'll never reach there, they'll never reach here, right? Not
so
even reach, but
outside this 18 billion light years is part of another universe.
Yeah, that's my way of thinking of what is multiverse. Right? Outside this 18 billion light years is part of another universe.
That can be in any direction.
Any direction.
So exactly. Multiple universes.
Exactly. There are multiple regions of the universe, right? Already we know, right, which are impossible to communicate between them. In that sense, I would say that.
Or otherwise, we could have particles traveling faster than light.
Exactly. Otherwise we'll need particles faster than light, and the reason that it happens is because of this accelerated expansion. Right? This wouldn't have happened if there is no accelerated if there is no dark energy. Because of the dark energy.
Because of the dark energy, we have these multiple universes.
Exactly, because you have accelerated expansion, right? So these far away regions are moving away so fast that even light signals cannot reach.
One of the lectures of you available in YouTube, you conclude that we should populate other universes also. So how could be possible ever? Because we cannot travel with the speed of light. Because we need to travel with the speed of light to reach the boundary of our universe. Then we need to travel faster than light to populate other universe. Then can we imagine?
Yeah. So what I meant is the following, that we, as I said, we can reach up to 18 billion. Suppose we populate maybe not 18 million light years, even 1 billion light years, right? Say somehow, okay, up that radius. Okay? So today they are all part of the same universe. But as the universe is expanding, those places are moving out farther away. So far in the future,
that will be in the other part.
That will be part of another universe, right?
Okay.
Then we will not be able to communicate with them. So it is in that sense that we can populate. We cannot go beyond 18 billion light years, right? So those are already out of our range. Right? But within this 18 billion light years, if we spread out, then eventually we will be part of different universes.
Okay. But one more problem, that is while we increase our speed and we reaches approximately to light, what happens to our shape according to Einstein's relativity theory?
Well, if you are in a spaceship, nothing will happen.
Nothing will happen.
I mean, if somebody is observing you from outside, right, they will see various distorted shapes. But the person who is traveling in a spaceship, nothing will happen, right? I mean, it will be like normal life.
Elon Musk biographers claim that he founded SpaceX in an ambition to colonize the Mars before a catastrophic asteroid event wipes the humanity out from this Earth. So far we could reach only up to Moon, and his ambition is to reach Mars. So how can we imagine that we can go beyond our galaxies?
Well, I mean, we never know what humans will do in the future, right? But my feeling is that if we ever reach other galaxies, it will not be us physically, right? I mean, one possibility is that the AIs will become so much more intelligent, then there will be no need for us to travel. Probably the AI will spread out, right?
AI will spread out.
Yeah, because they are, I mean, if they become more intelligent than us, right? Then
AI
why
will overtake us.
Exactly. So why do they need us? No, so they will find their ways to spread out.
So the current human beings will go extinct.
That's one possibility. Right? Maybe not extinct. They'll keep us for some other purpose, right? Just like there are many other animals in the world, right? who are they are not we are not extinct. Other possibilities that maybe they will still be useful, right? Maybe we have some capability that the eyes cannot have, and we have to spread out humans, right? Even then, my feeling is that the way it will be spread, right, is not by sending physical human beings, right? Maybe our DNA, right, or even maybe our genetic code, right? We may have mini robots carrying our genetic code to distant parts and then build human beings from there. So that's my vision of how we might succeed in spreading to other galaxies.
It is heard that many articles about you tell that you and your wife, Professor Sumati Rao, both dedicated your life to research and teaching, and you love your students as your children, and you lead a simple life. So, what message would you like to give to science aspiring students, especially theoretical physics area, since now the focus is mostly towards the applied science area to get jobs. So it's quite difficult to attain any research gain from theoretical area, that it needs some patience, and it will take long time to reach a level. So what advice would you give to people interested, to students interested in basic science?
Yeah, so I would say that if you are really interested in basic science, right, you should certainly try going for research. There are various options of changing it afterwards if you find that you don't like it. Right? And I mean, in basic science, you will not make that much money, but there are jobs. It's not that you don't get jobs. You will not get a job that will pay a salary that at the level of what you will get in industry, right? But as teachers and as researchers, you can make a reasonably good living, but you will not be able to make money, right? So with that, I mean, if you still feel that you are interested in basic science, you should really go for it.
For the time limit, let me stop here, but I would like to get another interview of you about the story of time next time.
Okay, thank you very
And
much.
thank you very much, sir, for sharing this much time for us and inspiring us.
Thank you very much. Thank you.